So we saw that velocity was the displacement divided by time, with a change in position as a function of time. Now we're going to look at acceleration, which is the change in velocity as a function of time. Just as velocity is a vector, acceleration is also a vector. Now let's start with average acceleration first of all, because that's sort of where we started with average velocity. Our average acceleration is always the change in velocity. What was the velocity when we stopped? What was the velocity when we started? At least when we ended, whatever measurement we're taking. What was it when we began whatever measurement we're taking? Divided by the change in time. The SI units for acceleration are meters per second squared. If you're using CGS system, it's centimeters per second squared. And for the US customary system, not used very much, but it's feet per second squared. So average acceleration, vector quantity, the sign of the velocity, just like displacement, indicates in one dimension what direction you're going. Our general convention is if we're moving from left to right, it's a positive velocity. If we're moving right to left, it's a negative velocity. So a negative acceleration does not necessarily mean that we're slowing down. Okay? Again, look at your velocity. What is your velocity doing? Is your velocity becoming more positive? Okay? Or is it becoming less positive? A more positive velocity indicates that the number is going up. So the acceleration, which is change, indicates an upward trend, an upward change. If the velocity is becoming less and less, if the velocity is decreasing, but we're still going in the positive x direction, that's what gets so confusing, you have a negative acceleration. Okay? Remember, change. If you're traveling in the negative direction with a negative velocity and you're speeding up, that velocity is becoming more negative. That again indicates a negative acceleration. It means that the acceleration vector is pointing in the negative x direction. Of course, if you're going more negative, you're going in the negative x direction, the velocity is becoming less negative, then that's a positive acceleration. So that's a little bit difficult for people to get used to in their minds. That your sign for velocity and acceleration don't have to be the same, because each represents a change of a different type of quantity. Velocity is a change in position. Acceleration is a change in velocity. So calculating the acceleration, again, if you're just doing average acceleration, it's fairly straightforward. What is your velocity at this point? What was it when you started out? Okay? If there's no change, there's no acceleration. In this case, we have a vehicle traveling 30 meters per second after it initially started at 10 meters per second. The total trip took 6 seconds. So we take the change in velocity, Vf minus Vi, 30 meters per second minus 10 meters per second. A car starts with 10 meters per second and ends up with 30, so final minus initial, and divided by the total time that this change takes place, 6 seconds. This is an acceleration of 20 divided by 6, 3.3 meters per second squared. Okay? All right. If you have average velocity, you can also use this to calculate what your if you have average acceleration, you can use this to find out what your velocity is. Average acceleration is the change in velocity divided by time. We turn this equation around and we multiply both sides by delta t, okay? Divide both sides by the average acceleration. We get that the change in velocity is the average acceleration times the time that goes by. Consider a person who starts from rest. So we're starting with an initial velocity of 0. It accelerates at a rate of 3 meters per second squared for 2 seconds. How fast is he or she running after 2 seconds? So here we do the calculation. We know average acceleration. We know the change in time. I'm going to multiply this to both sides. So we'll just have delta V on the left-hand side. I think I said divide by average acceleration. We don't need to do that here. So here's a new equation. We get a change, 3.3 meters per second, 2 seconds, multiply the 2. That gives us a total change that should be 6.6 meters per second. So they started at 0, and they end up at 6.6, a little error right there, meters per second for the change. And since the initial was 0, that's also your final. Just as we did for velocity, where we graphed position as a function of time, and so that the slope represented the instantaneous velocity, we can do the same for acceleration. Okay? If something is undergoing a constant acceleration, okay, it means that the velocity is changing at a constant rate. Since the rate is represented by the slope, anything with a constant slope is a line. So, in this particular case, we have the velocity increasing by the same amount over a given amount of time. It looks like for every 2 seconds we go up by 10 meters per second. So after 4 seconds we're at 20, after 6 seconds we're at 30, so on and so forth. So if we take the slope, 50 meters per second, after 10 seconds, that gives us an acceleration of 5 meters per second squared. Okay? This is the simplest case. Here, the acceleration is constant, so the average acceleration is also going to be the instantaneous acceleration. What about for the case where we graph velocity versus time and the slope is 0? Well, that indicates that the object's moving, but it means that no change is taking place. Here the object started at 0 meters per second, sped up at a constant rate to 30, stayed at 30, and then it accelerated even more. Again, with 0 slope, the slope represents how much change is taking place per unit time. No slope, no acceleration. So you can move and have 0 acceleration. Later on, we'll look at different cases where the acceleration will change. Most of what we do is the case of a constant acceleration, because we will see that according to Newton's second law, force is proportional to acceleration, and we keep the force constant, the acceleration stays constant. But graphically, if you look at something and the velocity is increasing, okay, at a faster and faster rate, okay, the slope is low here, then it's getting greater right there, that indicates an acceleration that is increasing. Likewise, you start with a larger slope, then less of a slope, graphing velocity versus time. That indicates a decreasing acceleration. Okay? Now, important to point out, what we graphed formerly when we calculated velocity was displacement versus time. This is velocity versus time, so it's a different situation. Average acceleration, we are, again, looking at 2 points, the initial point and the final point. Again, we're graphing velocity as a function of time. And average doesn't care what your acceleration was during any of the trip. It's asking the question, what was your velocity starting out? What was your velocity at the end? Average. Change in velocity divided by change in time. Okay? And again, this is what it looks like. Your average, sometimes you'll have a bar over this to indicate average. Change in velocity over change in time. Let's get through some of this. Again, it's a vector quantity. We talked about this. When the sign of the velocity and the acceleration are the same, the object is speeding up. When the signs are different, velocity is positive, acceleration is negative. Where velocity is negative, acceleration is positive, the speed is decreasing. So again, it's important to get used to the idea that acceleration and velocity are disconnected in the fact that the sign of one doesn't determine the sign of the other. Okay? Acceleration doesn't ask what your velocity is, it asks how it's changing. Okay. Instantaneous acceleration, okay, is very much a calculus type of concept here. Instantaneous acceleration, just like instantaneous velocity, asks, what is happening exactly right now? Okay? It takes the limit where we're sampling the velocity, where the time is going to 0. Okay? What is the rate that it's changing? And therefore, by calculus, it represents the first derivative of velocity as plotted as a function of time. Okay? The instant acceleration is the limit, where again, you're doing final minus initial, where the time is becoming infinitesimally small. Very much a calculus type concept. For our purposes, it's much better to just graph it and look at what the slope is at any point. Draw a tangent line. Now, we can see this represented, since calculus can be represented, or derivatives can be represented a number of different ways. The Leibniz notation, which is typically taught in calculus, will show the acceleration is the first derivative of velocity as a function of time, and therefore, because velocity is the first derivative of position as a function of time, we can also write it this way. The Newton notation, instead of using this d dt to represent the infinitesimal slope, or infinitesimal change, I should say, we use a dot to represent that first derivative. So velocity is the first derivative, the dot representing the first derivative with respect to time, of acceleration. Acceleration is the first derivative of velocity as a function of time. It also becomes the second derivative of position as a function of time. All right, here's a more important point. Again, you can connect this if you're taking calculus right now. These are great for using, to understanding calculus. But again, think about acceleration as being a secant line, going from the initial to the final point. That is what the average acceleration is. If we were to make those time jumps smaller and smaller and smaller until they're infinitesimally small, we go from a secant line to a tangent line. The tangent line is really what is the slope at that particular point. Graphically, that slope represents what is the acceleration at that point. Again, remember what we're graphing here. Here's velocity as a function of time. What is the slope at that particular point? Kind of strange to think about slope at a point rather than between two different locations where you can do rise over run. But that is one of the most important aspects of calculus. Again, looking at the relationship between acceleration and velocity, we'll do this with some motion diagrams and some graphs. In the previous case, we had a car going at a constant velocity. The red arrow represents velocity. And you see no vector representing the acceleration because the acceleration is 0. Each point in time, this car is traveling by the same amount. For positive acceleration, notice that the velocity is getting greater and greater because the distance traveled along each time interval is becoming greater and greater. Here the acceleration is the velocity is increasing, the acceleration is constant. Okay? Both are pointing in the positive x direction. Okay? Acceleration is constant, velocity is increasing. In this case, we're slowing down. Notice the velocity is large here and gradually gets smaller and smaller. We can think of this as the acceleration vector subtracting off more and more from this vector right here, making it smaller and smaller. Whereas in this case, it's like the acceleration was in the same direction. It represents change. It was adding more and more velocity. So you can have a positive velocity and a negative acceleration. You can switch this around and say, well, if we're traveling in the negative x direction, the acceleration would be positive and the velocity would be negative. Again, acceleration represents the change. What is the change that's taking place? Again, if we have constant motion and we graph distance as a function of time, that constant slope, again, distance, notice it's distance, not velocity, distance versus time, gives me this graph. However, if I graph velocity as a function of time, I'm skipping ahead. I'll get into this next example. This is the case where we're increasing as a function of time. Distance versus time, we have increasing slope. So again, constant motion, constant slope for distance divided by time. Increasing slope for increasing velocity, that's what it looks like. Now let's go to the velocity versus time graph for each of these. In the first case, notice just a flat line. Here, our acceleration is 0 because our velocity is 10 meters per second throughout the entire measurement. For the increasing velocity, okay, at a constant rate, you get this relationship right here. So again, it goes back to the whole idea. Your acceleration is the slope of velocity versus time. Your velocity is the slope of the distance as a function of time. Okay? Again, very, very important for free fall, which we'll be tackling later on. In free fall, our acceleration is constant. That will give us this curve, which looks like a parabola and is actually a parabola, for your distance versus time graphs. For your velocity versus time graphs, it will give you a constant slope like this. Let's take a look at an application here. Here we have the Falcon 9 Heavy. This is SpaceX's most powerful rocket. It's actually 3 rockets strapped together. And we're going to look at its position as a function of time and what the velocity does as a function of that. Now, to understand rockets, you have to understand they start out with a lot of fuel. When the engines are on, they're pushing more fuel at the beginning and then less fuel at the end. Here is sort of the flight profile. So we see the rocket goes up mostly initially, and then it starts entering its trajectory toward orbit. Even though it looks like rockets go straight up, they actually begin to bank, and most of their velocity goes in the horizontal direction rather than the vertical direction. So we see the boosters will cut off at some point. We call this BECO. The main engines will cut off at some point, and then the second stage will kick in. But this is basically the distance profile as a function of time. Again, I'm sorry you can't really see these small numbers. This is about, this is all in kilometers, and this is all in times and seconds. Notice again, when it's very heavy, it's loaded with fuel. There's a very small slope because initially it's not traveling so fast. As the rocket engines accelerate it, the velocity becomes greater and greater, and eventually, in order to reach orbit, it's got to hit about 20 times the speed of sound. And that acceleration is achieved from the thrust from the rockets. So again, here's a very good example, an application. Distance is a function of time. The velocity is the slope of this, and as the slope gets greater and greater, you can clearly see this rocket is accelerating. All right? Now, if we graph velocity as a function of time, ignore this green for a second, because the green actually represents the vertical component. The red represents the horizontal component. We'll look at the blue, which is sort of the combined of the two. We're graphing velocity as a function of time, so it's a little bit different from the other graph. And you see, here this slope is small when it's taking off. It starts at rest, so it's going to have to start out small. And the slope is getting greater and greater, okay? That indicates that the acceleration initially is small, and the acceleration gets greater and greater as the slope gets steeper and steeper. Then it loses the two side rockets, okay? Us pushing it, so it actually begins to slow down. But the main engine has less and less fuel in the tank. It's getting lighter and lighter, so the acceleration begins to increase again. Then the main engine's cut off. Then the second stage hits again. But when there's nothing pushing it, notice the acceleration is 0 because the velocity doesn't change. So this graph right here is really nice to look at, how the acceleration changes as a function of time. If we go even further, as the second stage is burning, as the second stage gets lighter and lighter, again, the acceleration gets greater and greater. So again, looking at the slope as a function of time, you can get an idea of what the acceleration is doing. In fact, if you want to graph acceleration, this is what it looks like. You know, the acceleration gets greatest right before the side boosters come off, then it starts speeding up again right before the main engine cuts off, it drops to 0. Second stage kicks in and the acceleration gets greater and greater, and the second stage runs out of fuel.